right?
The one I sent in the Discord is the old one. Yes.
Okay, so I'm gonna edit the description for that one, and it's gonna say incorrect link. And then Amog, can you send me the new Livesolve link whenever you have it? The one that we're streaming to, like,
Okay, I have a new Livesolve link.
okay, can you send it either on Zoom chat or on Discord?
Yes, I'm gonna put it in the chat. Oh, it's private message. I'll just send it to
Okay, I got it.
I just did. Oh, that's YouTube talking.
Okay, I think I got it. Okay, I saved the old one. So anyone that goes to the old one and tries to see it should get a link to the new one.
And that's in the chat as well. So I think we should be good.
Okay, I'm gonna edit the link on
Okay, we
this
have
so
live
that and
viewers.
hopefully nobody notices. All right.
We do? That's kind of insane.
Yeah, we have live viewers. So we should get started.
Yeah. Hey everyone. Can you all hear me? Okay, cool. We're the Integirls problem writing team. And we're gonna do a live solve of some of our favorite problems from the 2025 spring competition that you guys have all completed at some point. So we'll go around and introduce ourselves. I'm Harini. I'm the executive director for Integirls. I'm a junior in high school, or rising senior, I should say. And I'll pass it on.
I'm a Moog. I'm the co-head of problem development for Integirls. And I'm also about to be the outreach director for the new Austin chapter. I'm a rising senior, and I like to do geometry.
Hi,
Um,
Catherine. Oh, you can go
Go ahead.
first. Oh, okay. Hi, I'm Catherine. I'm the chapter head for Iowa Integrals, and I'm a rising senior, and yeah, that's all.
My name's Scarlett. I'm from Chicago. I'm a rising senior. I'm our director of problem writing and Chicago chapter head for Integirals. Yeah.
Hi, I'm Alex. I've been a problem writer for Integirals for like 2 years. I'm going to be the scoreboard and statistics director, and I enjoy good food. Yeah.
Hi, my name is Anna, and I'm a rising senior. I'm going to be the co-chapter head of Integrals Bay Area and also the tech director for Central Integrals.
Cool. So we're gonna go around and just sort of RNG the problems that we'll be doing. So we'll put them through like a random generator, and then select the problems that we're doing, which Mo has currently. So Mo, if you want to do the honors.
Okay, can y'all hear me? Uh, should I share my screen for this? All right.
So we selected our favorite problems from the spring competition. So they're all on that wheel.
I'm lagging. HS Team 15.
Oh, okay, that's me, I think. Um, so where's the whiteboard?
Share? I'll create the whiteboard.
Oh, it's on Zoom. Okay.
I think Mo's sharing it right now.
It says host disabled participant whiteboarding.
Oh,
Oh, don't worry about it.
Oh, whiteboard. Okay, okay.
okay.
All right. Let's see if my stylus works. Yeah, I disconnected. Okay. I guess I'm using my mouse now. All right, let's look at this question. High school team 15. Where is it? All right. Let me see if I can copy and paste it in. Dang it. Wait, paste as image.
Yeah, I think that's a Mac problem.
I'm on yeah, I'm on Mac.
Yeah, it's a Mac
Alex, I
problem.
got you. Which one is it?
High
Team
school team
15.
15.
High school team 15. Give me a sec. What? Okay, I can't upload anything anymore. Oh, never mind.
Okay. Do we have it?
Got it. Here.
All right, thanks. All right. Oh, I should have actually done the problems ahead of time. All right. So compute the remainder. All right, so my first idea here, this would be really embarrassing if I mess this up. My first idea here is to like group the twos and twos together. Purely because dealing with pairwise products doesn't look very nice. So I think this gives us like, oh, what, 2 times 4 plus, and then if you looked at 4 times 5 and 3 times 4, that would group to an 8. So that would give us 4 times 8 plus dot 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 all the way into the end, which is, oh, it's missing. I mean, okay, so we can set this equal to s is sum. And then you add I guess, yeah. Hmm? That's what I'm doing. You add 100 to every side, I think. Then you get 100 times 101. Oh my God, this mouse. Okay. 101 division. So that obviously goes there. Collapses into, I think, 2 times 2 squared plus 4 squared plus dot 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 plus what, like 100 squared? Yeah. Um, over 101 minus 100. And so from here, I guess, oh, wait, I gotta move this. So from here, I guess we factor out the 2 squared from every term. We get 8 times 1 squared plus dot 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 to 50 squared. Oh my God, this is horrible. I'll try plugging in my stylus after I'm done with this. So once we get this equation, I guess from here, sum of squares probably works. I forgot the formula. Wait, wait, hold on. Let me try getting this. N times n plus 1 times 2n plus 1 over 6. Oh my God, I'm so good at this. All right, so let's keep going. 8 times 51 times, huh? Oh, I missed 50. 50 times self-glaze is great. Yeah. What can I say? Over 101. Explaining as I go. Yeah. Okay, this is some horrible commentary, my bad. Yeah, well, like essentially, I guess I'll talk about the motivation from the beginning at the end, but over here, like what we do is like sum of squares because there's not really there's not really a nice way to get the sum of every single square. Even though it's like modular arithmetic, but there is a nice way to get it as a like a series of factors using the sum of squares formula, which is why I decided to multiply it. I could be just on the wrong track entirely and just saying random stuff right now, but I think this is right. So, hmm? I'm good. All right. So over here, I guess we can factor out 100. That's what, 4 times 51 is 204. 204 minus 1 is 203, which is 100 times 203. What are we looking for? We are looking for, okay, mod 101. which is equivalent to negative 203. Yo, we messed it up? What? No. You forgot to divide by 6? Oh yeah. Good point, good point. Yeah. So this is why you got to check your work, guys. I was actually testing all the viewers. Okay, anyways. Divide by 6. So that means on the inside product, you have to divide this by 6. Yeah. Um, okay. 204 divided by 6 is, let me
34.
wait. Okay. I was gonna do it. I swear I was gonna do it. All right, so this is okay. So this is equal to 100 times, how do I erase stuff? Do I just like, oh, there, I see. Let's swap that. So this is okay, so the inside 204 over 6 is 34 minus 1, 33. So it's 100 times 33 mod 101. 100 is equal to negative 1 mod 101. And you multiply negative 1 by 33, which should give you 68 as your final answer. Yippee. All right, I guess I should talk about some of the motivation for this question. I don't know, like in the beginning, it's kind of like you can play with some terms around real quick, but I don't really know. I just don't know any number theory techniques that could like kind of devolve this aside from just like grouping some terms together. Some common things to try are to like group adjacent terms, or you could group like opposite terms, like 1 times 2 and 99 times 100. You'll realize pretty quickly that actually I might just be wrong, but I think that pairing opposite terms like 1 times 2 and 99 times 100 doesn't really get you anywhere, mod 101, especially since the denominator is 101. So by pairing adjacent terms, you get to the square term, the square form, and from there it's just some algebra. But yeah, I guess we can move on to the next question.
Okay, so I RNG the next question, and it's high school indiv problem 3.
Wait, is that me?
Yeah.
Okay.
Mhm.
I can add the thing. Okay, so for this question, I guess the first thing you do if you're maybe not that experienced is to draw a diagram. So you can sketch out the coordinate plane and label the points. So 6, 9 is over here. This is where B is. And A is at 2, comma 6, which is here. And you're asked to find the coordinate C where the segment AB is divided into the ratio 6 to 1. So C should be around here. And this ratio should be in the 6 to 1 ratio. So if you didn't know the formula, you would probably just calculate, like draw the right triangle, and the point C would be at the point 2 plus 6/7 of the, I guess, difference in the x coordinates, which is 4. So 2 plus 6/7 times 4, and then the y coordinate would be 6 comma 6/7 times the difference between the y coordinates, which is 3. And if you calculate that, it's just 26 over 7 and 18 plus 42 over 7, so 60 over 7. And then you're asked for the sum of the coordinates of C, which is just 60 plus 26 over 7. Wait, did I make a mistake?
I think the
Oops.
first one would be 20 over 7, not 26 over 7.
Oh yeah, okay. Oops.
It would be 38 over 7.
24 plus
38 over 7.
14.
Yeah.
I can't do math. Okay. 38. So 98 over 7, that gives 14. And then the formula technically for a segment in the ratio mn with the points x1, y1, x2, y2 is basically like a weighted sum. So m over m plus n times x1 plus n over m plus n x2, comma, the same thing. So yeah, that's basically how you approach this problem. Oops. Okay.
All right. I randomly generated the next problem. It is MS Indiv problem 24.
Oh, yay, that's mine. Do you mind pasting in the screenshot?
Okay, I'll
I do
upload
not have the
the problem
screenshots.
here.
So the way I kind of thought about this problem is, so first, like just taking the problem at the grocery store, you can buy bundles of bananas of multiples of 3. How many ways can you get bundles summing to a total of 15 bananas? If the order that you buy the bundles matters. So the way I kind of thought about this problem is like if you have to buy the bananas in groups of 3 and you're getting a total of 15, I can actually just think of it as I'm trying to bunch like 5 groups of 3 some rectangles. I'm gonna make them yellow because they're bananas. And so if I let like, hold on. I'm gonna take 5 of them, right? And like let each of these be a chunk of 3 bananas. Then the way I'm gonna solve this problem is I'm basically trying to think about how I can like partition the bundles so that I'm getting kind of a distinct arrangement of bananas. So let's say I wanted to like the example arrangement, 6 and then 6 and then 3. I can kind of think of the fact that I'm taking these groups of 3 bananas, I'm partitioning off the first 2, I'm buying those together. I'm partitioning off these 2 and buying these 2 together, and then I'm buying the last bunch of 3 bananas on its own. So if I was going to kind of picture, like if I was in contest picturing how to solve this problem, this is how I would do the setup. I would group by 3, and then I would think about each kind of way of buying bundles as kind of being a placement of these dividers. Now, what's really interesting is that if I take each of these partitions, I could place a partition here at this first spot. I could place a partition at my second spot. I could place a partition at my third spot, and I could place a partition at my fourth spot. And so I can place each of these partitions, and I'll be able to see that any given placement is going to create a different kind of arrangement of bunches of bananas. So, for example, as we saw with the example given, 6 and 3, I know that I need to have that second divider and that fourth divider, and that's it. And similarly, if I told you I had the second and fourth dividers and no other dividers, you could tell me that I had bought bananas as like 6, 6, 3. So I can really just think of whether or not to place each divider. And each of those choices, if I kind of multiply kind of the ways to make each of those choices, that's going to give me my total number. one, I have the choice to place it or not place it. Same with the second one, same with the third one, same with the fourth one. And so total, I'm making 4 binary choices in order to create my arrangement of bananas. And so I'm going to have a total of 16 possible arrangements because there's going to be an arrangement where I say choose to place this first one, not the second one, not the third one, then the fourth one. And there's going to be an arrangement where I don't place the first one, but I place my second one, third one, and I don't place my fourth one. So that would be kind of how I build the intuition behind this question. And in total, I'm going to kind of multiply all of these together to get my final answer of 2 to the 4th or 16. Yay.
Okay, thank you, Scarlett. Our next problem is middle school team 11. I think that's Catherine.
Yes, sorry, I was looking for it. Okay. I can upload the image. Okay. Okay, so here we have Yolanda and she loves yogurt, and you can buy yogurts in size of 15 milliliters and 17 milliliters, and she wants 223 milliliters of yogurt. So how many ways can she do this? And the order of the sizes she buys the yogurt in matters. So for me, intuitionally, like my first idea here is to just like first ignore the orders, and where's the image? 15 milliliters and 17 milliliters. And she wants 223 milliliters of yogurt. So how many ways can she do this? And the order of the sizes she buys the yogurt in matters. Wait, can you mute? Sorry. Okay,
Oh, sorry, that's my bad.
You're good, you're good. Okay, so the image, have you found it? Okay, so basically my first idea here is to like try to see how we can get 223 milliliters of yogurt ignoring order. So maybe like you can do this by bashing, and basically we can just subtract multiples of 15 from 223 until we reach a multiple of 17, and that sounds kind of like tedious, right? So how we can do that is we can actually take mod 17. So 200, why is it like that? We have 223 mod 17, and we want to find this. Actually, if you note that 221 is 15 squared minus 2 squared is a multiple of 17 by difference of squares. This means that 223 is actually 2 mod 17. And with that, we want to find like how many multiples of 15 do we need to subtract in order to get 0 mod 17. So notice that each multiple of 15 is actually negative 2 mod 17. So we want to subtract 16, sorry, we want to subtract like negative 1 mod 17 numbers of 15, because like 223 plus 17 equals 16 times 15. Wait. Yeah. So basically we have this, and we want to subtract like 16 mod 17 multiples of 15. So for example, we can subtract 16 15s, which is 240, to get a multiple of 17, or we could subtract 33 multiples of 33 15s to get a multiple of 17. However, notice that once you subtract 16 15s, like if you just do, what the heck? If you just subtract 16 15s, which is the least number of 15s we can subtract to get to a multiple of 17, we have that 16 times 15 is actually equal to, what am I doing? 16 times 15 is actually, yeah, 16 times 15 is actually equal to 240, but 240 is greater than 223. So actually, we can't subtract a number of 15s to get a positive multiple of 17. So this means that there are actually 0 ways to even get 223 milliliters of yogurt with 15 and 17. So this means that there are 0 ways in total. even with order, and then we're done.
Okay, thank you, Catherine. The next problem is also yours again. It's middle school Indiv problem 4.
Okay, so that one. Okay, I'll just put it right next to it. Okay, so here we're asking what's the least integer that has a total of 9 positive factors. I'm on an iPad. What is the least integer that has a total of 9 positive factors? And when you think of like positive factors, like if you want a number that has n positive factors, for example, you should always think of the prime factorization first and the formula for a number of factors of a number. So if you have like p1 to the power e1, p2 to the power e2, and so on and so forth, the number of factors is e1 plus 1 times e2 plus 1 times e3 plus 1, and so on. So we want 9 factors here. So we have to think about like how we can split like the e1 plus 1, e2 plus 1, so that they all multiply together to 9. So we have 2 cases here. If we just have 9, then then we have to have some primes to the power of 8, and we want the smallest integer. So here the smallest possible one is 2 to the power 8, which gives 256. And then the other case is if we have 3 times 3. So we have p squared times q squared, where p and q are both primes. And the smallest 2 possible primes are 2 and 3. So we have 2 squared times 3 squared, which gives 36. Then we have no other cases because there are no other ways to like split 9 into numbers that multiply together. And here 36 is less than 256, so our answer is 36. Okay, and then the next question also happens to be me, which is great because the random number generator is really randoming today. Okay, so this is high school individual number 7. And high school individual number 7, we have x is a positive real number such that x plus 1 over x is square root of 85, and we want to find the value of x minus square root of, x minus 1 over x. And here, my first idea was to just solve for x, but once you solve for x, like you have this square root of 85, it's gonna look really ugly. So so if you solve for x, you're gonna get some like really disgusting equations, and obviously we don't want that. So we have to think of something like a little more innovative. So actually what you can do is you can square x plus 1 over x, and you're gonna see why that works in just a little bit. So if you square x plus 1 over x, what's convenient about x and 1 over x is that they multiply to 1. So when you square it, you end up getting x squared plus 2 plus 1 over x squared, which is just 1 over x squared. Why does it do that? What the heck? Sorry, technical difficulties. X squared plus 2 plus 1 over x squared. So by the sum of squares formula. And then notice that if you square x minus 1 over x squared, you get x squared minus 2 plus 1 over x squared. So they just differ by 4. So if you can just find x plus 1 over x squared, you can find x minus 1 over x squared. And that makes our life really easy. So we know that x plus 1 over x is square root of 85. So x plus 1 over x squared has to be 85. And then we have this is just 85 minus 4, which is 81. So if we take the square root, we should get that x minus 1 over x equals to plus or minus 9, depending on whether like x minus 1 over x is positive or not. But it says x is a positive real number, so x minus 1 over x should also be positive because x should be greater. You can prove that x is greater than 1 here, because if x is less than 1, then you have some issues where like it can't go, x plus 1 over x can't go higher than 2. So we know that x minus 1 over x has to be positive, meaning that x minus 1 over x has to be positive 9.
All right, Mug. Can you use, I think I'm next. High school indiv problem 18.
I'll get the image real quick. Give me a sec.
All right. Wait, where's my yogurt image? I swear I drew it. There you go.
Okay. Here. Can you see this?
Yeah, wait, let me move it next to the yogurt. All right, there you go.
Where's the
All right.
yogurt?
It's right here. Dude, I drew it when we were doing the yogurt question.
Oh.
Yeah, yeah,
Okay.
yeah. All right. So this question. A happy number is a number that can be written in that form. How many positive integer values for k are there such that the roots are happy numbers? Okay, well, so we know that k is a positive integer, right? So that means if we're looking at the discriminant, right, we have the quadratic formula x equals 18 plus or minus the square root of 324 minus 4k, right? Oh my God, this is horrible. Over 2. And well, basically we noticed that the discriminant can't be a negative number, otherwise it would be complex, right? So since it's positive integer, that basically means that k is lower bounded by 1, and it's also upper bounded by, I think, 81. And basically, well, I guess there are two forms here. I think that we either have b is equal to 0, in which case it's just x equals a as a root. Or we have b is not equal to 0, and we have that 324 minus 4k is equal to, actually, wait, no. I think, okay, there's a nicer way to do this with completing the square, but first I'll just simplify this. Let me move this down real quick. All right, there you go. So x is equal to this. It's equal to 9 plus or minus, and then you get the 2 out. You factor out the 4 from the inside. You get square root of 81 minus k. Yeah, there you go. Bro, Amog, what are we doing? Okay, whatever. Wait, do I pause until? Okay, yeah, whatever. Um, yeah, so you get that it's equal to the form 9 plus or minus the square root of 81 minus k. Uh, so if we have b equals 0, if we have b equals 0 in the happy integer form, that means that the inside, basically 81 minus k, this implies that 81 minus k is a perfect square. Perfect square. And then if b is not equal to 0, that means that we have like the inside is the square root. 81 minus k is equal to square root of 2 times b squared. Let me just write that. So that means that 81 minus k equals 2 times a perfect square. Okay. So what does that mean? That means that, well, we have the two forms, so we can just start counting. So 81 minus k equals perfect square. There are 9 values, I think, for that, because we have the squares 0 squared, 1 squared, dot, 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 9 squared, as our value for 81 minus k is equal to that. But also notice that k cannot be equal to 0 because it's a positive integer. So 9 squared is gone. We have 9 values. If we have 81 minus k is 2 times a perfect square, we have it's equal to 2 times 0 squared, 2 times 1 squared, dot, 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 up to 2 times 6 squared, which is, let me think, is that 7 values? Uh, so that means that the answer is 16. Can you verify? Probably was off by 1 somewhere.
you double counted 0 somewhere, I think.
Oh yeah. Oh yeah. So, oh yeah, zeros here. Yeah, so that's actually 6 values, which means oh yeah. So yeah. Which means we have 15 total values. Yippee. Smiley face. There we go.
All right, thank you, Alex. RNG just gave me what did RNG give me? I think I put it in the chat. Did I do this? Wait. Oh yeah, HS indiv problem 20. Kareem, that's you.
Okay, cool.
I'll put the image in.
Thanks. So this one is fun, Geo.
Okay, here it is.
Cool, thanks. Okay, so for this question, we're gonna start by drawing a diagram real quick. Because you always draw the diagram. So A, B, C, and we're gonna try not to make A, B, C equilateral or isosceles. Because that is a pitfall. Or right, as I seem to be making it. What is wrong with this? Okay. There we go. So A, B, C. Point D divides the side AC. 1 second. Okay, D divides the side AC in the ratio 3 to 5. So we're gonna put D about there and draw BD in. E is the midpoint of BD. That's about the middle. And F is the point of intersection of the lines BC and AE. If you draw a line through E that goes to C, there's our point F. So if we have point F, my bad. So given that the area of the triangle ABC is 880, what is the area of triangle EBF? So if the area of triangle, so the area of a triangle is its base times its height divided by 2, right? So if two triangles share a base, then the ratio between their areas is the same as the ratio between their heights, and vice versa. If they share a height, then the ratio between their areas is the same as the ratio between their bases, right? Because the area is base times height divided by 2, right? So we're going to use that to find first the area of ADB. So this is how we mark, you can mark area by putting brackets around it. So the area of ABC is 880. The area of ADB, so ADB and ABC have the same height, right? That's just the height from B to AC. But then AD has 3/8 of the base of ABC. AD is 3/8 of AC. So then ADB has 3/8 of the area of ABC. So then the area of ADB is 330. We can do the same thing to get the area of BCD, because CD is 5/8 of AC, right? So then the area is 550 because it has the same height as ABC. So then once we've done that, you can work towards EBF by first dividing this into 2 more triangles like that. And then we can solve, so within BCD, which we know is 550, so we start within ABD, which we know is 330. We know that BE and ED have the same length. So if BE and ED have the same length and AED and ABD have the same height, then the area of AED should be equal to the area of AEB, if that makes sense, right? And we know that these sum to 330. So individually, they each have to be 165, right? And then now we have ratios for, one second, sorry, technical difficulties. Yeah, what's going on? Okay. So now we have ratio, we have those numbers, right? And then we can go into BCD and label some things. So we know based on what we just did, sort of an analogous thing is that EBF and DEF should have the same area because they have the same base and the same height, right? But we don't know what that area is, so we're just going to label it X. Similarly, CDF is 550 minus 2x because we know that the area of BCD is 550 and the area of BEF and DEF are both x, right? And now we can use our ratios again. And I'm going to really quickly port all of this work over so I can keep writing under this problem and hopefully stay within the frames with YouTube. So then we can write another ratio, right? That basically that uses the area ratio between yeah, so it uses the ratio of B of CF to FB, right? So we know that the ratio of CF to FB is going to be the same as the ratio of the area of the triangle CDF to BDF, right? Because those two have the same height, which is the height from D to BC. And we also know, so I'm going to try and actually, I'm just going to like highlight those areas of the triangle to make that more clear. Sorry, this is a bit of a lengthy explanation. So the ratios that we can use are the ratios between this triangle. So the ratios that are all equal to the ratio between CF and BF are the ratios between this triangle. So the light orange triangle and the slightly darker orange triangle, or the same orange really. So yeah, the darker orange and the lighter orange. And then also the darker green and the lighter green, right? So so hopefully that makes some sense. Because those ratios are both the ratio between BF to FC, right? And so then the length ratio from BF to FC is equal to the ratio between 2x, which is the area of BFD, to 550 minus 2x, which is CFD, which is also equal to the ratio between 165 plus x, which is the area of BAF, to the area of FAC, which is equal to 715 minus x. So this leaves us with a pretty neat equation to solve. And our final answer, we just want to solve for x, which is the area of EBF, right? So if we solve this equation, we can just multiply. We can cross multiply to get an equation to end with, which we end up with 1430x minus 2x squared equals 550 times 165. I'm not going to multiply that out right now because that is long. Plus 550x minus 330x, so which is plus 220x minus 2x squared. And this is not actually a quadratic. Wow, that's a really messy 2x squared. This is not actually a quadratic because our x squared terms cancel out quite nicely. And then we can solve for the rest of this. So we end up with 1210x on this side is equal to 550 times 165. And then you can solve that out to get x equals 75 by factoring. And so because we want the area of triangle EBF, you can solve for 75 for your answer. You can also do this with something called mass points or with some other thing called barycentric coordinates, but this is the most approachable solution that basically uses the same concepts.
Okay, thank you, Harini. Now it is my turn to present high school individual problem 23. So I have a diagram to go with this, and let me find a diagram really quick. Okay, here it is. So the points A, B, C, and D lie on this circle omega with center 0, such that A, D, and O are collinear. The distance from A to BO is 9, the distance from B to CO is 10, and the distance from C to DO is 11. And we want to compute essentially the radius of omega and then square it and take the floor. So this diagram is not to scale, but this length is 9, this length is 10, and this length is 11. So I guess what really first comes to mind here is trig, but I'll present a solution that does not involve any trig. The first step is actually to reflect everything inside the circle over the line AD to get more stuff inside the circle. Essentially filling up the circle, and I'll show you guys why this is very useful. Let me pull up the second image. Okay, so this is what it looks like after we've done this reflection. As you can see here, we now have 6 lengths, which I will label here. And we can think of each of these wedges of our circle as, say, pizza slices. And the point here is that these pizza slices are essentially movable. We can rearrange the order of the pizza slices while maintaining the circle and its radius. So I'm going to rearrange the pizza slices in a way that makes the problem substantially easier. We'll label the pizza slices to avoid any confusion. I'll just label them, say, A, B, C, D, E, and F. Okay, now let me, here is how we can rearrange these pizza slices. Let me label these. This is C, this is D, this is E, this is B, this is F, and this is A. And so essentially by moving around, oh wait, never mind, sorry. Yeah, no, this is correct. Essentially by moving around these pizza slices, we've turned our problem into a much simpler problem in which we have a triangle. We also know the side lengths of this triangle because these two lengths are 11. So the length CD will be 22. Similarly, the side lengths of the lines in slices B and E are 10. So this side length is 20. And the side length with A and F will be 18. So I'm going to remove the letters from this diagram. My bad. I'm trying my best. Yeah, whatever. So I've tried to remove the letters from the diagram. And the point is that essentially what this boils down to is finding the radius of a circle circumscribed about a triangle with side lengths 18, 20, and 22. So here what we're going to do is we're going to use a formula which states that in a triangle with side lengths ABC and area capital A, then we have A is equal to ABC over 4R, where R is the circumradius. So we can rearrange this to get R is equal to ABC over 4A and square this because we want to compute the floor of R squared. At this point, we want to substitute the area of our triangle in, and the fastest way to do this is to use Heron's formula, which states that if S is the semi-perimeter of a triangle, then the area of the triangle is the square root of S times S minus A times S minus B times S minus C. So we can disregard the square root here because we're squaring our expression. So this becomes ABC squared over 16 times uh, S. By the way, S is a semi-perimeter, which is half of the perimeter. So in this case, S would be 30. And I'm not going to go through the calculations here, but we end up with R squared being equal to 1089 over 8, which is also equal to 136.125. So our final answer is 136. Let me choose the next problem really quick. Okay, it's high school team 10. So that is also my problem, I believe. So let me uh, delete all of this. Also, I think Alex drew a pizza.
I drew two actually.
Two, yeah. Okay, here's the problem. Yeah, compute the last three digits of 431 times 681 plus 819 times 931. Now something is going on here. We're not going to multiply these numbers out, which is one solution path, and I'll present a different solution path instead. So you might notice that 431 plus 681 plus 819 is actually equal to 1,931. So this motivates us to, number one, add a 1 in front of this 931, which doesn't actually affect any of the last three digits of our product. And it also motivates us to, number two, one second. It motivates us to put our numbers on a number line, or as segments on a number line. So we'll plot points A, B, C, and D such that AB is 431, BC is 819, and CD is 681. And what we want to compute is AB times CD plus BC times AD. Now, a formula of this sort might look familiar to some more experienced problem solvers. There's a theorem called Ptolemy's theorem, which states that if the points A, B, C, and D are the vertices of a cyclic quadrilateral, then this product is equal to AC times BD. But we have a line here that's not a cyclic quadrilateral. Or is it? You might notice that the points A, B, C, and D lie on a line which is a circle of radius infinity. Alternatively, another reason that you can think of ABCD as a cyclic quadrilateral is because the angles ABC, which is 180 degrees, and the angles ADC, which is 0 degrees, they add up to 180. So anyways, armed with this new knowledge, we can actually use Ptolemy's theorem to extract the value of the sum of these products. So the length AC is equal to 1250, and the length BD is equal to 1500. And the funny thing about this product is that we don't have to compute anything because this number has 1 0 and this number has 2 zeros. So its product will have 3 zeros. And yeah, the answer is just going to be 0, 0, 0. Okay, our next problem is going to be MS Indiv problem 10. Who is that? One
That's
second.
Scarlet.
Oh, it's the domino question.
Okay, should I do it or do we want to
Yeah.
just skip it? All right. Okay, our next problem is middle school Indiv problem 10. How many ways are there to arrange 5 red dominoes and 5 purple dominoes such that there are no 2 uh, red dominoes in a row? So the way we're going to do this is essentially we're going to look at the possible configurations for the red dominoes, and then we can just fill in the blanks for the purple dominoes. So oh, Scarlet back. Okay, Scarlet, do you want to present
Back.
this? Never mind. Okay. Um, so we have, I'm going to, what I'm going to do is I'm going to draw 10 blanks. And then we'll put R or P in the blank to denote red or purple. Okay, Scarlet is back. Scarlet, do you want to present?
Yeah. Sorry, it's still like loading. My
Cool.
internet
Okay.
is completely dying. But I think this problem is really interesting because like I'll be able to use the whiteboard and kind of diagram it out in a sec. But the way I kind of thought about this problem was basically first I can think about kind of placing my red dominoes, right? So I'm gonna again use some kind of rectangles. So if I have a red rectangle, like let that be a red domino. Um, hold on. And I'm gonna get 5 of them. Um, so I have all 5 of these, right? And then I want to kind of arrange my purple dominoes. And when I set up my purple dominoes, I want to make sure I never have 2 red dominoes in a row. That's basically what the question says. But the way I can do that is I have my 5 purple dominoes. And what if I kind of place them so that here, this is purple. So this is the purple domino. I'm going to take one of my 5 purple dominoes and I'm going to put it in that slot. And then I'm going to take another purple domino. I'm going to put it in that slot. Another purple domino in this slot, and a final purple domino in my last slot. So in doing this, in placing kind of 4 out of my 5 dominoes in these positions, I know that I'm going to avoid having any red dominoes in a row. And then since I have 5 of each kind of dominoes, I still have 1 more purple domino to place. So I could place that purple domino before any of my red dominoes. I could place it in my first place, my second space, my third space, my fourth space, or I could place it after all of my dominoes. So in total, that's going to be 6 positions for my purple domino. So that's going to end up being my final answer. I'm going to make this really big. So that's going to end up being my final answer because of those 6 positions. And then the way we can rationalize just that we're not going to be kind of overcounting or undercounting there, is because like each placement would create a different arrangement, right? So, and I should also justify the reason that we don't have to say account for what if we placed it before or after the original purple domino we put in each spot We don't need to do that. That would actually be overcounting because either way, if we have kind of two dominoes, like between these first two red dominoes, it doesn't matter if I place another purple domino in this spot before the domino I'm moving around right now or after it. The result's going to be the same. I'm going to have two dominoes in this spot. So I can kind of think about and rationalize the fact I'm not overcounting, not undercounting. If I place an extra domino in any one of these four spaces, um, then that's going to create kind of a double domino, and that's going to be unique with regard to all my other configurations. And then before or after, again, it should be pretty easy to see, like you either start or end with a purple domino, and that makes it unique. So I'm not going to be overcounting any cases there, and I can very confidently conclude that my answer is going to be 6.
Okay, thank you, Scarlett. We'll finish with one more problem and then, uh, yeah. Okay, so the next problem or the last problem will be the last problem on the high school individual test or high school individual problem 30. It's a pretty difficult problem as far as I know. I don't know anyone who's solved it, but I will present the solution here. Let me pull up a diagram really quick. Okay, here's a good diagram. So I have a trapezoid ABCD with parallel bases AB is equal to √3, CD is equal to 2 √3, and the height is 6/5. So we're given that the sum of the angles CAD and CBD is 180 degrees. And we want to find the difference of the fourth powers of AD and BC. So the way we're going to approach this is we're going to factor this AD to the fourth minus BC to the fourth expression into AD, that's a P, AD squared minus BC squared times AD squared plus BC squared. And so we'll first compute this second expression, AD squared plus BC squared. For this, we're going to need a new diagram. One second. Here. So what we've done here is number one, we've intersected AD and BC to get this new point E. And number two, we've called the intersection of BD and AC G. Now let me explain a little bit of the intuition behind doing this. We know that AB is half of CD. So if we intersect AD and BC to get this point E, then A will be the midpoint of DE, and B will be the midpoint of CE. And you can think of it this way because essentially a dilation with a scale factor of 2 at E will send the segment AB to the segment CD. So we've labeled the intersection G, which normally stands for the centroid, because in fact, this point G is the centroid of triangle ECD because it is the intersection of two medians of the triangle. So anyways, I'll draw these medians in again. We have that this angle ACD plus this angle BCD is 180 degrees. And so we also know that this angle EBD, this angle, which I'll draw in here, plus the angle BCD is 180 degrees because they just add to a straight line. So this means that the angle EBD is equal to the angle CAD. Also, similarly, we know that angle EAC is equal to angle BCD. So I'm going to clean up the diagram really quick. But the point is that using the angle equalities, we get that this angle EAC is equal to the angle CBD. And the angle CAD is equal to the angle EBD. And so from this and our equality, we know that angles EBD plus EAC is 180 degrees. But if we look at the quadrilateral EAGB, we've shown that its opposite angles add up to 180 degrees. And in other words, that means it must be cyclic. So I'm going to attempt to draw a circle around these 4 points. This diagram is not to scale, so the 4 points are not actually cyclic. Here we go. So we're given an angle condition. We kind of turned it into I guess, a circle condition, but we want to compute lengths. So our next step is to use power over point at point D to just get a length equality. So from this in a cyclic quadrilateral, we know that dA times dE is equal to dG times dB. So I'm going to turn this into, I'm going to turn all of these side lengths into variables. So number one, I know that CD is equal to 2 root 3, but we'll let that be X for now. Also, CE is, we'll let that be Y, and we'll let DE be Z. So because BA is half of DE, the left-hand side becomes 1/2 Z squared. And also DG is 2/3 of DB. So the right-hand side becomes 2/3 DB squared. Now there's a theorem that you can use, which is essentially gives you the length of median. And this essentially tells us that DB squared is, let me see if I can remember this. It is X squared over 2 plus Z squared over 2 minus Y squared over 2. No, minus Y squared over 4. That's the theorem. So if we expand everything, we'll end up getting that, and I won't go through simplifying all of this, but we end up getting that Y squared plus Z squared is equal to 2X squared. And we know that X squared is 12 because X is 2 root 3 from the problem. So 2X squared is 24, right? And also Y is 2 times the length BC and X is 2 times the length AD. So this becomes 2AD squared, or sorry, 4AD squared. Plus 4 BC squared equals 24. And so we can divide both sides by 4. And we know that AD squared plus BC squared is 6. Okay, so this is the first part of our problem, right? We found AD squared plus BC squared. So I'm going to erase all of this work and I'll replace that with the value 6. Right, so now we need to find the value of AD squared minus BC squared. And let me pull up another diagram. So you might notice something here, and that's that we actually haven't used the altitudes yet. And so, or the length of the altitude from the top base to the bottom base, which is given as 6 root 5. So we're going to drop altitudes from A and B and try to use these to compute AD squared minus BC squared. So the way to do this here is you'll notice that AD squared equals AM squared plus MD squared. And we also have that BC squared is equal to BN squared plus NC squared. So also AM equals BN because these are both the altitudes. So if we subtract here, we'll get AD squared minus BC squared is equal to MD squared minus NC squared. So now we're going to do something, I guess what we've done before is we'll write this as the difference of squares, but we'll do this in a slightly interesting way. So we'll let MD, the length MD be N, and we'll let the length NC be N. But we're going to do this in a directed sense. So in other words, I guess we can let DM be M and so we'll define the lengths dm equals m and nc equals n. And the motivation behind this is that, or rather, what we're going to do here is set dm to be a negative length because it's pointing towards the left, and nc will be a positive length because it's pointing to the right. Now, in this diagram here, I've created it so that n lies outside segment CG, and we actually don't know that this is true. It ends up being true, but we can use directed lengths in a way such that it doesn't matter whether n is to the left of d, in which case small m is negative, or m is, say, over here, in which case small m will be positive. So anyways, this quantity md squared minus nc squared is m squared minus n squared, which factors as m plus n times m minus n. Now, the quantity m plus n is very easy to compute because it's just the difference between sides a, b, and c, d. So that's just root 3. M minus n is substantially more difficult to compute. And let me walk you guys through how to do it. So essentially, we have the quantity m plus n. So we can also use this to compute the quantity m plus n squared, which turns into m squared plus n squared plus 2mn. We also, using the Pythagorean theorem some number of times, we can compute m squared plus n squared. And so using, I guess, an arithmetic sequence, we can compute the value of m squared plus n squared minus 2mn, which is equal to m minus n. Squared. And then using that, we can find the value of m minus n, and then we're actually just done with the problem. So this first value, m squared plus n squared plus 2mn, is just going to be equal to 3 because we know that n plus n is root 3. Now we want to compute the value of m squared plus n squared. So to do this, I'm going to go even further down here. So remember that by the Pythagorean theorem again, m squared is equal to ad squared minus am squared, right? And n squared is going to be bc squared minus bn squared. Right now, we can actually compute the value of this quantity. And that's because we know the sum of AD squared plus BC squared from before. That's just 6. And we also know that AM is just 6 over 5. And BN is also just 6 over 5 from the problem statement. So we will subtract 2 times 6 over 5 squared, which is 72 over 25. So in the end, we get that m squared plus n squared is 78 over 25. So I'll put this down over here. Now, one thing you might notice is that this actually tells us that m lies outside segment CD, because you might notice that m squared plus n squared is greater than m squared plus n squared plus 2mn, which implies that 2mn is negative. So in other words, one of m and n must be a negative length. But anyways, moving on. These are the first two terms of our arithmetic sequence, and we want to compute the third. That becomes 81 over 25. And we know that this is n minus n squared. And miraculously, or not so miraculously, it turns out that this has a nice square root. So we know that n minus n is the square root of 81 over 25. Which is 9/5. So going back to our product over here, we can replace the expression n minus n with the value 9/5. Right, and so this product is 9 root 3 over 5. So we know that AD squared minus BC squared, which is this value, is 9 root 3 over 5. And we can also substitute this value into our original expression up here. And so this is the value of AD to the fourth minus BC to the fourth when I put it in absolute value marks, I guess. Oh, notice that we haven't really been paying attention about the actual sign value of this quantity in all of these calculations. I've just ignored it. This is because actually if I like take my original diagram and say flip it about the perpendicular bisector of CD, then the value, I can essentially swap the values of AD and BC while the problem conditions still hold. So we have to ask for the absolute value of AD to the fourth minus BC to the fourth here. Anyways, this turns out to be 54 root 3 over 5. Going back to the problem statement, it's asking for m root 3 over n for positive relatively prime integers m and n. Our m and n is 54 and 5. And so our answer is 59.
All right, I think that's all our problems.
Cool. Thank you so much, everyone, for watching. We hope you enjoyed learning to solve some of these problems. Have a great day. We'll do more live streams in the future, and we'll also be posting some more solutions of problems to our Instagram account, which you should follow. It's int.girls, I believe. So that's INTE.girls. So go follow that, and you'll see more problems over the next couple of months.